Welcome back to Honors Calculus. In this video, we're going to finish up our discussion of the coordinate plane with the ideas around transformations of functions. So let me get my head out of the way and let's dive right into it. In the written notes, I have all of these ideas carefully written out as theorems. I'm going to completely avoid that discussion for the moment and go right into some examples. I want to take a look at a function defined by the graph y equals f of x. So if I very carefully draw out my coordinate axes, and I sketch a curve on top of these axes, which might look something like that, I can identify the key points of the curve. This point down here, an x-intercept, seems interesting. Right here, we have a relative maximum, a peak on the graph. We have a y-intercept and an x-intercept relatively close together. We have a trough down here, a relative minimum, and then I have another x-intercept. And if I know the coordinates of those points, say -5, 0, -3, 3, 0, 1, 1, 0, 2, -1, and 4, 0, that's enough information for me to get the general picture of the function, and that's enough information for me to play around with what the graph is going to look like. So the idea of a transformation is to create a new function by adding, subtracting, multiplying, or dividing this function by something somewhere in the argument. I might want to graph y equals f of x minus 1. The new function here is called a transformation. In this particular case, is called a horizontal translation. I'm going to take each point of my function, and it's going to slide, in this case, to the right by 1. In other words, if I want to evaluate f of, say, -5 to get the point -5, 0, well, I'm now evaluating f of x minus 1. So x minus 1 is -5, which means that x itself is -4, one spot to the right of where it was in the original graph. Doing this for every point on the graph, -5, 0 is going to become -4, 0. -3, 3 is going to become -2, 3. 0, 1 is going to become 1, 1. 1, 0 is going to become 2, 0. 2, -1 is going to become 3, -1. And 4, 0 is going to become 5, 0. And the graph is going to take on the same basic shape, or within my ability to draw it in that same basic shape, each point just sliding over to the right by 1 unit because we have a 1 right there. All right. I'm going to copy this original graph, y equals f of x. So we have the same graph of y equals f of x that we had before. And now let's look at y equals f of x plus 2. Here, the addition happens outside the argument of the function. So when we perform the transformation, it happens to the value of the function after it's been evaluated, which is going to cause things to either shift up or down. In this case, they will shift up by 2. So if I draw out my coordinate axes again, this time all of my x coordinates are going to stay the same. All of my y coordinates are going to increase by 2. So instead of -5, 0, we're now going to be looking at -5, 2. Instead of -3, 3, we're now going to be looking at -3, 5. Instead of 0, 1, we're going to be looking at 0, 3, 1, 2, 2, 1, and 4, 2. Otherwise, the curve is going to more or less take the same shape. Again, my ability to draw the same curve taking the same shape notwithstanding. And we have the exact same curve, just sliding it up 2 units from where it was originally. All right. Let me copy that graph one more time. I'm going to make use of it once more. This time, I want to take a look at the graph of y equals 2 times f of x. Now I am multiplying all of my y values by 2, which is going to give me a much taller graph. Right? No longer is this a translation. This is now what's called a scaling or stretching of the graph. Nice property that the scaling has is that the x-intercepts all stay at the same place. It is only points away from the x-axis that are affected at all by a scaling factor like this. So -5, 0 is still -5, 0. -3, 3, doubling that y coordinate of 3 takes it to -3, 6. 0, 1, doubling that 1 takes it to 0, 2. 1, 0 is at the same place. 2, -1 is now at 2, -2. And then 4, 0 is still at 4, 0. All right, so this graph looks very similar, but kind of stretched out compared to what we had before. The important thing to notice is that again, the x-intercepts stay at the same place. my horrible artistic ability notwithstanding. The idea of transformations of graphs should be something that you are already familiar with. This particular type of transformation, where the points will change when they are away from the x-axis, but on the x-axis the points don't change, is going to be something of use to us. I'd like to take you now to a piece of web software called Desmos, D-E-S-M-O-S, as you can see right above me. The URL is desmos.com, and it is a free graphing calculator available to anyone, and you're able to export and create images, include those images in documents, and it has a couple of very nice features for us. So as we are thinking about graphing, one of the things I want to pay attention to is the fact that we can use computer software to produce a graph for us. And the computer software is going to answer a number of questions that we might have in the graph, but it's also going to introduce some questions that we're going to have to answer through other means. So if I simply click over here and bring my cursor up, I can type in any equation or function, and Desmos will go ahead and graph that function for me. Oops. That's what I wanted. Let's take a look at f of x equals 3x cubed minus x squared minus 2x. It's a nice cubic function. Looks kind of similar to the one that we were working on by hand. Well, that is great. What I really want to do is graph some transformations. So I'm going to tell it that I really want to graph y equals a times f of x, f of x plus b plus c. And Desmos asks me if I want to introduce some sliders. Let's go ahead and introduce all of those sliders, and we'll start playing around with things. I can deselect this icon right next to the original f of x to get that blue curve out of the way so that we're only looking at the transformation. And I can play around dragging the slider to get b and c both 0. And you can see if I plug in a equals 1, b equals 0, and c equals 0 into that equation, I have the original function. I'm also going to go ahead and zoom in a little bit so that we can get a little bit more detail out of this graph. One of the things I like about Desmos is that this slider allows us to play around with what happens as you change the value of a, right, the amplitude or the scaling factor. And we can also see pretty nicely, not only can we grow this thing to the point that you can't even recognize it anymore, but as we go towards 0, right, multiplying the value of the function times 0 kind of just flattens everything. But that transition lets us go into the negatives, where we get the same curve, just upside down. Right, let's go ahead and reset that at 1. Right, the value of b, as we add, it shifts things to the left. And as we subtract, as we add a negative value, it shifts things to the right. And finally, of course, c shifts things upward and shifts things downward. All right. If I click on the graph, you can see kind of faintly a couple of dots come out. if I click on each dot individually, it will give me the coordinates for that point of the graph. Here is where Desmos is both incredibly powerful and incredibly useless to us. Finding these values is nice, but what you'll notice is that most of them are horrible, ugly decimal approximations. Right? That maximum occurs at negative 0.373, 0.451. That is a hideous number if ever I've seen one. Our goal in this course, one of the things we're going to be looking at is how do we find the exact value of that point, the exact value of that x and y coordinate. We will be addressing that question later on in the course. For now, I just want to point out that that is something that is a distinction between what Desmos can do and what we can do on our own. The other thing I want to point out that Desmos can do that I am going to be asking you to do in this course is up here. I can get that to stay there. There we go. There is a share graph button. And when you click on that, it gives you options to print out the graph if you have a printer available, or to export an image of the graph. I do want to point out that as soon as I did that, all of the coordinates on the graph did go away. That is something that does happen. So if you want those specific coordinates, you may have to do things a little bit differently. But on the assignments, I am going to ask you to include graphs. Exporting an image here and uploading it into D2L is a great way of doing that. All right. Graphing tool aside, let's go back to our notes, because I've got one last topic to talk about on transformations of functions. We say that a function is periodic with a period called tau if and only if f of x is equal to f of x plus tau for every x in the real numbers. And you're familiar with a couple of periodic functions already. Sine, cosine, tangent are great examples of periodic functions. What I want to point out with periodic functions is that if you have a function f with a period of tau, then it also has a period of 2 times tau, or 3 times tau, or 4 times tau. And the proof of that is fairly straightforward. If we consider f of x plus 2 tau, we can rewrite that as x plus tau, right? That's the definition of 2 tau. And I can group that as f of something plus tau. And the definition of period says that f of something and f of something plus tau are the same. So this must be equal to f of x plus tau. And then by the definition of a periodic function, Since f has a period of tau, f of x plus tau is the same thing as f of x. So f of x plus 2 tau is the same thing as f of x. A function that has a period of tau also has a period of 2 tau, and we can do this to also prove 3 tau, 4 tau, or in general, n times tau for any integer, positive or negative, n. So periodic, something you should be familiar with. It will come up a little bit in this course. The trigonometric functions, certainly functions you should be familiar with. But what I really want you to do is to spend some time playing around with Desmos. Right. So use Desmos or similar software to graph y equals 3 times the sine of 2x plus 1. And once you've done that, identify its y-intercept using the graph. So take a few minutes, get on to the internet, find Desmos, or if you have another piece of graphing software that you like using, use that software to graph this function, upload an image of the graph as your assignment for this video, and we'll see you in the next one.